Okay, good day everyone. Let's continue our discussion about numerical methods root finding solution. So, in the last video we have discussed regular falsi method or false position method. So, this video is focused on another iterative process in finding the numerical solution of root finding methods of a function using Newton-Raphson method. Okay, so Newton-Raphson method is another method of finding the root of nonlinear equations, which is faster than that of the bisection and regular falsi method. It is used to determine a root of an equation by using the first few terms of the Taylor series to evaluate a suspected root, a point of tangency of the curve, and a suggested line adjusting it iteratively to obtain a better approximation of the root. So the first derivative of function f of x is provided and it should be existing and continuous. The method is suited for functions which slopes are not steep, such that only few approximations of the root already lead to an accurate estimate. Okay, so we have here the figure of representing the Newton-Raphson method. So we have here the x-axis and the y-axis. So considering this is now the graph of function. Okay, this is the graph of the function. Say this is f of x. Okay, so let f of x be a function. So and let p be a root of the equation f of x equals 0. So starting from the initial root be 0. So actually if we have a function here f of x, so intuitively we have a root here. So this process or this method is particularly you are drawing a tangent line, say from this point, say tangent line. So meaning tangent line is tangent to the curve of function of x. Tangent meaning touch to the curve. Okay, so the tangent line must always cross the x-axis. So take note of this dotted red line. It is always crossing to the x-axis and it is tangent to the curve. So with that, P1 is determined and the sequence continue. So let me discuss this. For example, this is the initial or the initial approximation point. Okay, so this point, drawing a vertical line here, we have coordinates here in this point. We have xi 0. So focus on this point. So we have xi 0. Okay, and then this one we have say here. So this is xi function of xi. So this point, particularly this point. Okay. So this point xi fxi. Okay. Noted that for example, if we draw a tangent line here, we can get the slope of this tangent line, say represented by theta. Okay, this theta. Now, if we get tangent theta, we all know that tangent theta is the slope. Okay, slope of this tangent line. We have f prime of xi is equal to tangent theta, which is equal to, for example, if this is point 2, okay, point 2, and this is point 1, or you can say point 1 or point 2, or point 1 or point 2, say. So using the formula of the slope here, I'm presenting this one, say tangent theta, so it's a y2, so y2 here, f of xi minus 0, so y1, okay, all over xi minus xi plus 1. So meaning the iterative process from this point will be this one will now be point 2. The coordinates of this point 2, or the approximation of the root that converge to this root, is the point of these coordinates is xi plus 1, 0. Take note that we have to begin I equal to 0. Okay. Now, if we have to continue this one, okay, so take note that this is the formula. So this formula is focused on this tangent line. Okay. So let us continue. Okay. This is the graph we have presented. This is the graph for illustrating the Newton-Raphson method. So, for example, if this is the tangent line, we have this equation. We have already get this equation from the previous slide. So therefore, if I have to simplify this equation, I have this. Okay, and then if I have to simplify further to get xi plus 1, just cross multiply this one. Okay, and then say simplifying, this is now the iteration process to get the xi plus 1, and so on and so forth. Okay, so what are the steps to follow? This is the steps to follow in finding the root of a function using Newton-Raphson method. First, you have to calculate f prime of x. So what do you mean by calculate f prime of x? So meaning this is derivative of the function. Okay. The next step, which is number 2, is choose an initial guess x of 0. So you have to put initial guess here, x of 0. So anything, example, x of 0 equal to 0, or x of 0 equal to 1. So that is your initial guess. So your guess will be correct if it converge, or if it is diverge, your initial guess is wrong. And then last step 3 is evaluate this one. We have already get this one. For example, start at 0. So therefore, if you start at 0, so x 0 plus 1, so we have x 1, and then x 0, f of x 0, then f prime of x 0, and then that is a continuous process. Say sample at I equal to 1. So therefore, if I equal to 1, so this will be x2. So this will x1, because our I is 1. x1 minus f of, that is x1, and then f prime of x1, and so on and so forth. Okay, until xn. Okay, so therefore that is xn plus 1. This is xn plus 1 rather. So xn plus 1. So that is xn minus f xn f prime of x to the xn. Okay, so this is the formula, and then after which you have to evaluate f prime of xn, f prime of xi, or f prime of xn, and so on. And then you find the error that is denoted by this formula. Xi plus 1 minus xi all over xi plus 1 times 100. So check if the absolute value of error is less than that of the pre-specified tolerance. Okay, so to have this, we have to show example to present what is Newton-Raphson method uh, behind. So I have example here. So find the root of a function f of x is equal to x5 minus 20 using Newton-Raphson method up to 3 decimal places. So let x 0 equal to 1, so meaning this is now the initial guess. Okay, back here. Using the steps. Okay, so first is you have to calculate f prime of x. So therefore, if you have to derive this function, f of x equal to x5 minus 20, the derivative of this function is 5x4, because if we derive a 20 that is constant, that is 0. Okay, next step would be choose an initial guess x0. So we have here x0 equal to 1. Okay, if I have to evaluate the f of x0, so therefore I am evaluating f of 1. So if I have to evaluate f of x0, okay, so merely that is equal to f of 1. Okay, so I have to substitute. So 1 raised to 5 minus 20, that is negative 19. Okay, minus 20. So negative 19. Okay, this one. So after deriving this function, so I have get 5x4. So therefore, if I have to evaluate f prime of x0, this one, take a focus of this one. So f prime of 1 equal to 5, correct? Okay, now from the formula that is, say, the formula is x1, because we have to start, say, this is the formula. Okay, xi plus 1, xi minus f of xi all over f prime of xi. Okay, so therefore, let me write the formula. So this is xi plus 1 equal to xi minus f of xi all over f prime of xi. Okay, so therefore, so we should start our iteration at 0. So let's say I equal to 0. So therefore, if I is 0, that is x1. So that's it. Yeah. Okay, say x1. So therefore, x of 0, what is x of 0? 1. So x of 0 minus f x of 0 all over, this is all over f prime of x of 0. Okay, so therefore, so to prove that the x1 equal to, so this x0. So our x0, that is our initial guess here. So x0, 1. So minus. So f of x0 is negative 19. So negative 19. So f prime of x0, we have evaluated already that. This is the result. So we have 5. So evaluating that one, that is equal to 24 over 5. Okay, 24 over 5. Okay, this one. This is the result if we evaluate x1 using this formula. Okay, so we will continue. So we have to evaluate f of x1. So f of x1. So you substitute this value. Say f of x1. So f of x1, that is in decimal notation, that is 4.8. Okay, 4.8. So f of 4.8. Okay, so f of 4.8. So that is we back to the function here. Okay, focus on this function. So f of 4.8. So therefore 4.8 raised to 5. Okay, 4.8 raised to 5 minus 20. So the result will be this one. Okay, now, so again, if we evaluate f prime of x1, uh, you have to, here, this is the equation of the derivative. Okay, so f prime of x1. Okay, 2654.208. So you can check that in your calculator. Okay, now, so let us solve for x2. Okay, so x2, again, or to solve for x2, so for x2, so our I here is equal to 1. Okay, because we're done with 0. So next of 0 is 1. So therefore, back to the formula. X 1 plus 1, that is x2. Correct? x2. So therefore, so xi, so therefore x1. And then minus f of x1. F of x1, and then again f prime of x1. So as you can noted and observe, this is a continuous process, or that is a process of iteration. So therefore, x2 is 24 over 5. So x1 is 24 over 5 here. Okay, this one. So x1. So x1 is 24 over 5 minus f of x1, which is this one. Substitute here, all over that one. So we have a value of x2, that is 3.847535204. So again, if we have to evaluate this x2 using this one, you can get this value. Okay, so just substitute this value of x2 to this equation. Okay, can get the value of this f of x2. Similarly, for f prime of x2, this one, you can get using this equation. So as you can see, this is an iterative process. Now, continue. Let's x3. So for x3, we have say x2, because in x3. So for x3, we have I equal to 2. Okay, for x3, I is equal to 2. So therefore, looking in the formula, this is xi plus 1. So xi plus 1, that is x2 plus 1, that is x3. So x3, that is equal to xi, that is x2, minus f of x2 all over f prime of x2. Okay, f prime of x2. Okay, this one, x3. So again, if we have manipulated the value by substituting x2, particularly in this equation here, so we can get the value of x3 by substituting x2 here, x2, and then f of x2 here, then also f prime of x2 here. So we have get already the value of x3. So therefore, evaluating again f of x3 to this equation, can get this value. Okay. Again, if we have evaluated this value using this one, we can get also this one, and then x4. So for x4, this is now the I here is equal to 3. So it is recommended to use a table format of this, uh, particularly in the iteration process. You can write as a, say, I0, say, for example, you can write a table, for example, I, okay, so we have xi, okay, so therefore, for example, 0, what is x0, okay, what is x0, say xi, this is xi plus 1. So again, it 1, say x, okay, this is wrong, this is, if I0, this is x1, okay, if I equal to 1, this is x2, and then so on and so forth. 2, I equal to 2, this is x3. So put the value there. So I think you should also put the value of error here. Specified error should be less than or equal to the specified tolerance error. Okay, that's it. Let me go back here. So we have already find x4. So continue, we have to solve f of x4. Again, use this equation, and then for the derivative, use this equation also. Okay, so we have x5 here. Okay, and then again evaluating, we have already also get the value of f of x5 and f prime of x5, which is necessary in solving for x6. So therefore, an x5 we have equal to 4. Okay, so that is the fourth iteration. Okay, so I equal to 5, x6, we can get the value of x6. So I equal to 5. And solve again f of x6, f prime of x6. And then we can get value of x7, that is I equal to 6 here. So as you noted and observed here, the values we get for x6 and x7 is merely the same. Again, continuing this process, f of x7, f prime of x7, using this value we get, we have also get x8. Okay, so x8 using now I equal to 7. Okay, evaluate f of x8. As you noted that our results of x7 and x8 is the same, particularly the same. So let's have another iteration. For example, at I equal to 8. Okay, this is x9. Now, as noted, x7, x8 is 9 is now have the same value. So therefore, we have made the conclusion that this value is the root of the function. Okay, because as you can see, by evaluating f of x9, say this one, f of x9, f of x8 is approaching to 0. So our f of x is now approaching to 0. Okay, and then similarly, uh, if we have another iteration is equal to 9, I equal to 9, I equal to 9. I equal to 9, so we can get x10. So x10 is the same with x9 and x8. So therefore, if we evaluate f of x10, that will be approaching to 0. Okay, so take note, this function, if you look at f of x equal to x5 minus 20 is a degree of 5. So meaning we have roots, we have 5 roots to determine. Okay, so the root we have find is the one root that is the real root of this function. Okay, the other root of this function may be determined by using different initial guess. Okay, so in the next slide, I have graphed this in MATLAB. So this is the graph of the function x5 minus 20. Say, so again, this is now the x-axis. This is the x-axis. As you can see, this is 0. So this is the x-axis. X-axis. Okay, and this one is the y-axis. Y-axis. Okay, take note that the root we have get using this method, the Newton-Raphson method, we have find the root. This one. This is 1.8205. So the value of the root that we have find is 1.8205. Okay, as you can see in the graphical approach using MATLAB, this one is this value. Okay, so if we have to substitute this value, let us say f of 1.8205, this will be 0 using this function x5 minus 20. So x5 minus 20. Okay, evaluate this function. So therefore, we find the root of this equation, x5 minus 20. So the root of this function is 1.8205. So we check, you can check this value in your calculator, and that is the function of this 1.8205 will be 0. Okay, so that's the end of my presentation using this Newton-Raphson method, and then we'll continue this on the next iterative process in numerical methods solution uh, using a fixed point iteration method. So that is the root, another root finding solution. So thank you everyone and God bless.